So my project is on counting solutions to polynomials over a finite field of numbers. And not only is this a mathematically interesting question, but it also has applications to coding theory, specifically in error-correcting codes. I'll talk about the applications of my project at the end of this presentation. To set the background on projective space, I'm going to ask the question, at how many points do two distinct lines in the plane intersect? Typically, the answer is 1, but it could be 0 when those lines are parallel. But that's unsatisfactory because we'd like it to always be 1. So we'll introduce a point at infinity such that these two lines intersect infinitely far away. You can view this through the lens of perspective drawing. So these two railroad tracks are parallel, but they do intersect at this point in that drawing. So what does projective space as a whole look like? So if we have those two parallel lines from before, they intersect at that point at infinity. But we have to include a circle at infinity for all possible directions of those parallel lines. So projective space looks like this plane, and then extending it into the circle at infinity. And we like to think of points through coordinates. So I've labeled all the coordinates here. And one thing to notice about them is that they use colons, not commas. And the reason for that is because all we care about are the ratios of the numbers, not the numbers themselves. So the point 336 is the same thing as the point 112. And that means we can always make the first coordinate either a 1 or a 0 by scaling. If it is a 1, then those last two coordinates will just define the point on the plane like normal. And if it's a 0, then we're at the circle at infinity, and those last two coordinates dictate the direction. So this point is 0, 2, 7. And that actually means that all the lines that pass through it have a slope of 7 halves. And again, 7 halves is a ratio, so it's the same as 14 over 4, which is why this point is also the same as 0, 4, 14. So as you can see, those colons represent that this space is invariant under scaling. So this is the formal definition of projective space, and all that you really need to know here is that we need, this definition just formalizes the idea that points are equivalent under scaling. And one thing to note is that when you have m dimensions, you actually need m plus 1 coordinates. So even though we're in the two-dimensional case of the plane, we do need 3 coordinates to describe all the points there because we extended the space. So my project works in weighted projective space, though, and that's a generalization of projective space. So this is also the formal definition of weighted projective space. And the difference here is that every single coordinate now has a positive integer weight that dictates how quickly it scales. So instead of the point 115 going to 2 to 10 by scaling up by a factor of 2, I have to scale by 2 to the 1, 2 to the 2, and 2 to the 3 if my weights are 1, 2, and 3 to yield 2, 4, 40. Notice that when all the weights are 1, then we recover our definition of projective space. In my project, however, the numbers that I use aren't going to be integers. They're going to be elements of a finite field. So a field is a set of numbers that have the 4 basic operations. And examples of those are rationals and the reals, as we're used to. Non-example is the integers, because, for example, 5 divided by 2 is not an integer anymore. A finite field is just a field that has only a finite number of elements, and if it has q elements, we'll denote it fq. An example of a finite field is fp, where p is a prime, and that's just the integers mod p, so performing modular arithmetic, so always taking a remainder mod that prime. The last topic that I need to introduce is what a hypersurface is, and those are just the set of roots of a polynomial. So say we have the polynomial p in xy that's defined by x squared plus xy, where both x and y have to be elements of the field with 5 elements. And so the field of 5 elements is just the remainders mod 5. So if I make those remainders negative 2 through 2 instead of 0 through 4, just so that I can put the origin in the middle here, these are all the values that I plug into this polynomial. So for example, if I plug in 1 and 1, I get 2, because that's 1 squared plus 1. And then the hypersurface right here is just simply the set of the roots of the polynomials. So just the set of points that when you plug it into the polynomial, you get 0. And the natural question to ask is, how many points can be on a hypersurface? Or how many solutions can you have to a polynomial? And that's analogous to the fundamental theorem of algebra that states a degree d polynomial in one variable can have at most d roots. But the issue is we do have multiple variables, and we're working in weighted projective space over a finite field. So the fundamental theorem of algebra doesn't actually apply. So let's take a look at an example for how many points can actually lie on a hypersurface. So if I have this example polynomial here, f of xyz, where that's defined as x squared plus xy plus y squared. So actually, the variable z isn't in this equation, but I'll still say it's in the polynomial. And because we have 3 variables, that means 3 coordinates. And as I explained before, we always have 1 more coordinate than we have dimension. So that's why we're in 2-dimensional projective space. And I'll say it's over the finite field with 7 elements. So this is a degree 2 equation because it's a quadratic equation. We have order 7 because we have 7 elements in our field. And our dimension is 2 because we're in 2-dimensional projective space. So these are our zeros, and there are 15 of them. If you write it in this form, we can actually express them in terms of d, q, and m like this. That turns out to be the maximum that you can have, so the maximum number of solutions you can have to a polynomial. And that was proven in 1989 by Jean-Pierre Serre. And so this inequality just shows that the number of solutions must be no more than this number. Again, this is in projective space, though, and my project is in weighted projective space. So in 2017, Aubrey and collaborators made a conjecture that this bound would generalize into weighted projective space. So as long as your first weight is a 1, and then you store all the other weights, which are positive integers, in increasing order, then all you have to do is just divide by a1. But they were only able to prove this for the 2-dimensional case. Also note that when you set all the weights back to 1, you go back to projective space, and that's Serre's inequality again. So as I said, they were only able to prove it for the 2-dimensional case, and my project is trying to generalize that result into higher dimensions. So I proved this following theorem that has to make a few more technical assumptions. So for example, I have leading ones instead of just a single one. And that means that a1 is 1, so it disappears from the inequality again. But this theorem does apply to any dimension, not just dimension 2. And so we see that the bound that was expected from Serre's inequality does generalize into weighted projective space. If you actually plot the values of the number of solutions you can have, you can get a graph like this for these parameters right here. And this line, this dashed line right here, indicates the bound I just proved, because the number of solutions can't exceed this line, that value. But one thing you do notice about this graph is that there are only very discrete values that you can have as the number of solutions. And so we observed this pattern, and so we set out to try to prove something about it. And we proved that it has to satisfy this modular congruence, that the number of solutions has to be congruent to 1 mod p. We actually conjecture an even stronger result, that it has to be congruent to 1 mod p to the k, which would better represent the actual spaces, these gaps that you see in these possible values. So as I said in the beginning, this project does have applications to error-correcting codes. And an error-correcting code is a way to transmit a message with additional redundancy so that you can correct errors during transmission. And the key things to consider in an error-correcting code's performance is its capability to be resilient to errors versus the additional length that you actually need to add to give it that resilience. Weighted projective Reed-Muller codes are a type of error-correcting code that uses polynomials in weighted projective space. And they have been demonstrated to be higher performing, so they have a better resilience to errors per additional length that they add than other types of Reed-Muller codes. And Reed-Muller codes are widely used throughout the world for error correction, and they are related to Puller codes, which are the 5G standard. But actually being able to quantify the resilience to errors for a Reed-Muller code is pretty difficult. And what ends up happening, because it uses polynomials in weighted projective space, is that its worst case performance is dictated by the maximum number of solutions you can have to a polynomial in weighted projective space, which is precisely what my project was about. So by creating the upper bound, I can actually say what the worst case performance of a weighted projective Reed-Muller code is. And given that they are widely used throughout the world, that's pretty interesting.